The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
So our next speaker is Ivan Diaz-Loya from CeraTech, and he is going to talk about reactivity analysis of high calcium fly ashes for non-traditional binders. Ivan?
Good afternoon, everybody. Well, what I want to share with you guys today is just a small study that we did at CeraTech. I did this along with Carlos Orozco from Argos. We were basically looking for a couple of reactivity indicators for the fly ash that we use. We use high calcium fly ash, but basically we needed something beyond pass or fail. So just to give you an overview of the technology, we obviously have a much simpler process. Many of the ready-mix plants that we use, they already have Class C fly ash in place. So we take our activators, which are non-caustic and they're renewable, and then we mix them at the power plant. We hook them up just like they do with any admixture, and that's it. So it's a much simpler process. Does this work? So we were looking for a quality control tools that we could actually set up the power plant or before basically the ready-mix plant. So we need something, again, beyond pass or fail. We know that Class C works and Class F will not work for us. We want to be able to deliver concrete with consistent set time and strength. And by quantifying the reactivity, we can quantify changes also in the mix. So if we know how much the reactivity changed, we can quantify how, the amount of change that we have to make in our activators. So we could be able to deliver not only a unique product, but we can deliver quality and we can deliver consistency. So I think we all know what fly ash is, but I'll say it anyways. Main components are silica, calcium oxide, aluminum, iron oxide. Class C fly ash also has pretty high contents of magnesium oxide. Mostly amorphous, higher amorphous content than Class F fly ash. Crystalline components, most people would agree that they can be considered relatively inert. Mean particle size on average, we have around 20 microns. And most people also would agree that the reactivity depends on the glassy phase content and the glassy phase composition. So what we did, we took 20 fly ash samples that we were using commonly, from low strength to higher strength. We ran chemical composition, crystallographic characteristics by XRD, qualitative and quantitative. We also did the particle size distribution, obtained the particle size distribution of the fly ashes. And we used a couple of glass manufacturing parameters, which are the alumina saturation index and the non-bridging oxygens per tetrahedron. They are calculated directly from the oxide content as measured by XRF. And the response that we used was compressive strength at 1 D. That's a terrible slide, so I apologize, a bunch of numbers there. But what I want to show you here is just a range of chemical compositions. As you can see, alumina varied from 15% to 20%. Silica from 29 to 37%. That was probably the highest range. And the calcium ranged from 24 to 30%. That's the crystallographic characteristics. As you can see, the amorphous content ranged from around 65% to almost 90%. I don't have here the crystalline phases because, as I said, they can be considered relatively inert. That's the particle size distribution. Also, just to show you that they were pretty close together. There wasn't any big differences in the physical characteristics of the fly ashes. But here, as you can see, the differences in compressor strengths were huge, from 2,000 to 6,000 psi. So that's a big difference for such a short range in variability in the chemical composition. So what we did was to run a stepwise regression. Basically, we took all the possible regressors. So basically the oxides from the chemical analysis, LOI, non-bridging oxygens per tetrahedron, the amount of glass. We also considered the calcium to alumina ratio, the mean particle size, the alumina saturation index, and the sum of silicon plus iron plus aluminum. And so as you can see here on the y-axis is the correlation factor, R squared. And here on the x-axis, what I just told you, right? So as you can see, the alumina saturation index came out to be one of the main parameters that influences the compressor strength, followed by non-bridging oxygens per tetrahedron and the calcium to alumina ratio here. So just a little bit of basics. These parameters are widely used in glass manufacturing, right? And basically, in glass manufacturing, you have two different kinds of components. You have network formers and you have network modifiers. The network formers have a valency of +4, so they can form tetrahedrons. They can be linked with 4 oxygens, and each oxygen is acting as a bridge between the two network formers. So you have a network kind of like this one, right? But here, let me back up here. The network modifiers can only be linked with 1 or 2 oxygens because of the valency, right? So they don't form bridges, so that's why they call them network modifiers. The interesting thing here is the relationship between the aluminum and the network modifiers because of the valency, the +3 valency. As long as there's aluminum there and there's network modifiers, the aluminum is going to take these network modifiers and they're going to be acting as charge balancers for the alumina so that it can be combined with 4 oxygens until all the aluminum is saturated. So once all the aluminum is saturated, then the network modifiers can actually be acting as network modifiers. And then the more network modifiers you add to your network starts to look more like this one. It's a more fragile network. So pretty basic formula. We calculated that from the XRF analysis once again. These were the results that we obtained. I should also mention that once we saw that we were getting good results with this, we added 18 more fly ash samples. So at the end we had 38 fly ash samples. So when we plot this with the compressor strength, this is what we get. So for example, here an alumina saturation index of 1 would be that all the aluminum is fully balanced and your network is looking more like this, right? There's more polymerization in the network and it's more stable network. So once your network modifiers start to go up, or the amount of calcium usually is what starts to go up, then you have a network that looks more like this one, more fragile glass, a more disrupted glass that is more reactive. And we can see that the compressor strength is actually going up as your alumina saturation index numbers drop. And the same here for the non-bridging oxygens per tetrahedron. So as with any model, we have a number of assumptions and restrictions. Basically, the first one is that we assume that we have no crystalline phases. Obviously, that's not true. There are crystalline phases that are inert there. We also didn't consider the free energy of hydration. We considered that the physical characteristics are constants. We didn't take that into account. Obviously, there's variability there. We also consider that the material is homogeneous, and it's really not. The chemical composition of each fly ash particle will vary it will vary from particle to particle, basically, and what we see on the chemical analysis of the fly ash is basically just an average of all the chemical compositions of all the particles. We also assume that iron is always acting as a network former, and that's not always the case, depending on the burning conditions. It can be iron 2 or iron 3, so that would change things a little bit. Also, we didn't consider the phosphate concentration. That also can have a big influence on the glass network. Titanium could substitute silicon in a fourfold coordination. We didn't consider that either. And here on the bottom, you can almost see it. SO3 interactions. We didn't really consider SO3 interactions. That's also something that could have an influence there. However, despite all the assumptions, it seems to work very well. So in practical terms, we have this surface graph where you can locate the reactivity of your ash, A, B, C, or D. A being the most reactive ash, to D being the lowest reactive ash. So you can locate that here. The alumina saturation index is on the x-axis, and the non-Bridgen oxygen per tetrahedron is on your y-axis. So we also came up with this quality control report. You input basically your chemical analysis, and it'll give you a projected compressive strength and a projected grade that we can then match with our in-house performance-based test that Raj you will see a presentation from him this afternoon. He developed our standardized in-house test. So we can match now the chemical analysis or the potential reactivity from the chemistry of the ash to our performance-based test. That's it. That's all I have. Gracias.